Yeah, just a quick introduction. I'm Koiro and I'm back with another video, and this was the video I was filming when I fell and broke my leg, and it actually stated the reason why I broke my leg, because I broke my leg when I was on my way out of the doctor's office, because I have been troubled with my elbow here for quite some time, and that's why I have not been making many videos last year. But this video is kind of interesting. It does have some 4000 series logic and some discrete logic fault finding, and it's in some ways a continuation of a video I did before, but I have my own intro in this video, so this is just a short introduction to tell you that this is a video that everything was filmed, and actually the card was chipped away just the day before I broke my leg. So I think I've put too much work in this video to not publish it, but everything you see here is from August and no, it's from September and no, I don't think October and November, I think is the right way to put it. October and November last year. So let's get on to the November Koiro and hear what he has to say about this project. Hi, this is Koiro, and long time no see. I have been struggling a bit. I do have some inflammation in some muscles and some joints in my arms, so I have not been able to edit video really. So that's my main thing, and also this affects my ability to work on electronics and stuff. But lately I have gotten better, so that at least I can work with electronics, and if I can still edit video, we have to see. And today I'm going to look into something like this, and this is a board from coin game, what we in Norway call a knipsekasse. You can see it up here. This is a video that actually is posted on YouTube from the fellow that actually owns these cards, and he sent me several of these cards for one game that's called a SilverCoin, and I have repaired one of these boards before. There is a link to the video below, or videos, and this is board primarily made out of 4500 and so on series of C-Mos chips, and this is logic that is not using standard TTL levels, that is 5 volt and nowadays 3.3 volts or even lower, but it was able to use logic for up to 18-20 volts on some of these chips. And I have gone into depth how this logic works, and I have also gone into depth and explained the logic diagrams of some of these chips in my last videos. I'm not going to do this here, so just let's jump straight to the bench and see what we can find out with probing around with my logic probe. Yes, today we are going to look at this, and what's inside here is actually some cards from a Norwegian coin game, what we used to call a knipsekasse, whereas you are playing actually with the coins that you put inside. And this is two cards that both have not the same fault, but both are faulty. And I just picked this up, and I'm going to unwrap this, and we are going to take a look of what we have. Yeah, when you're shipping old electronics, it's very important to wrap it good and to have a stabilizing core so it doesn't get bent. And also these are C-Mos logic, so it's very important to not pack them in something that generates lots of static electricity without having something to short that out near the board. I do have a message, and it's probably written in Norwegian. And here we do have the cards themselves. Oh, it's 3 cards. Okay, and they are marked. Be careful not to lose the marks. 1 card. And another one that's identical with another message. And a 3rd card. Oh, this is actually 4 cards. Okay, then we have our work lined up for us, and I'm going to read what he has to say about these cards. And here he says this is a parts card. Earlier this blow diffused once, and Tommy at Arctic Retro has actually been looking at this. And the card is still dead and has an unknown condition. And we can see that this card has some missing parts. There is missing one IC here. And this is not populated, have never been. So there are some slight differences between these cards. And also you can see that if they use this to a temper switch normally, they are placed a bit different. So these cards are not entirely the same. Yeah, there are lots of other differences too, but probably a lot of the parts are the same. So we are going to put the parts card aside for now. And this says digit and display is okay. No signal on the counting and payout, and no magnets are activated. Magnets is the solenoids that's on this, and you can see here they have used transistors, probably with some silver alloy or something. And these, because you can see they have got really black. Yeah, there are some shine in these cards, of course. And if I take the next card, is this identical? This numbers display okay works. Last hit shows last hit, but the magnet only hits 1 time. Whatever, so it's only counting to 1, and you have to restart the game, and the same is happening. Without restart, it doesn't hit the magnet of its own, and that means that some counter or another is not counting. And this card is also not exactly the same. This is more the variant that is on the part card, I think. But these cards are probably interchangeable. But let's look at the last one. And this one says minus on the last hit, no counting, and magnets. And what we can see on these cards, they are using C-Mos logic, and I have another video on the Lars Berg coin game on my webpage, and there you can see some more theory about the C-Mos chips from way back when. These are normally run by from 5 volt to about 18 volt, some of them, and most of them at least is running to 15 volts. So they are doing this logic, I do think the power supply on the last games was about 14 volt or something. And that is my main issue here, is that I need to be doing some debugging first to see what inputs we have on the voltages here. And you do have 24 volt here, you have 12 volt, 0 volt, and you do have some other outputs. So on the other game I do had to jump some of these contacts to make the counting work, but that has to be something we check out eventually, because first order is to see if they are working the same. And these two cards are the same. They do have the same kind of temper switch. This has the other temper switch, and this doesn't have the temper switch. Yeah, it does have. So this game, is this the same as this one's? Just take a quick check. Yeah, they do look about the same, but there are some differences. You see, you have the placement of the IC is the same, but you can see down here you have all these knobs here. They are not on this card, so there are some differences. And you can see this is the version 2264 and this is 2263. And let's see on the others if there are some numbers here too. This is the 2263, so this is same version, and this one, it does not have this kind of version numbers at all. 2261, so this is version 1, and this is the parts card. So there are variants of the same card, but slightly different. And we can also see that the logic handling is probably also not the same, because here you can see this probably is a working game, but it doesn't have as many logic ICs here as the other cards. So probably they did issue some error that was impossible, or they did extend the counting or something on the newer versions. But I'm going to rig a power supply, and 12 volt is probably for the logic, 24 volt is for these outputs to the solenoids, and 0 volt is of course ground, and these are probably connection points for some of the other heavy draws here. And what we did encounter with the other card I was looking at is that there was several oscillators on the card that was just C-Mos gate delay oscillators made by Smith triggers, and they was mixing on the ICs to make some random counting actions, and it's probably the same on these cards. So I do have to dig in and look at my earlier video and check what's going on. There the oscillators was run by 2 potentiometers, and here you also have 2 of them, and you have these rotary switches here that probably are for doing adjustment for how far up they should count. Yeah, here you can see also that this plug here has not all the leads populated. This was the version 1 card, so probably the game itself didn't have as many opportunities. But these C-Mos circuits are very prone to static electricity, and what we encountered last time was that some of these, at least one of these chips, was easily destroyed by just measuring on them and using the noise from the power leads. And one of these chips actually did work with low voltage, but when you increase the voltage to 12 volt, it did work on about 9 volt, I think it was, and then when I increased the voltage, one of the outputs on the counter stopped working. So first line of action is to actually identify all these chips, what they are, and get the data sheets. So I'm going to start there. In the attached documentation I found this, and it's of course in Norwegian, but here it's stated what is coupled to where on this card. And in A it says it's contacts for the opto couplers, and this is open opto couplers that detects when a coin is passing by. And B is for port switches, it's this one. And C is for the display card, and this is some multiplexing action going on, probably, I'm not sure. At least on the order, there was one counter that was counting which counter should have the numbers, so it was time multiplexed. And D is sensors in the coin payout trenches, and the E down here is the magnets or solenoids. And F is contact for counter. F is down here actually. I'm not sure if this is an output. I do think it's an input for the counter. And yeah, because you have the card also have counters to detect how much money is in the game, because you have one counter that counts the payouts and you have one that is counting how many coins are put in. So this is the pointer for the how much is in the box, the coin box, and this is G is for payout, it's this one, and H is for counting input. Yeah, and this is the 12 volt, 24 volt, and static and something. It's not even here. It should be here somewhere. Maybe it's on some of the others. And this they call a tilt switch. It's the temper switch, and it probably should stay away, and if it's touching, then it's a tilt. So this one should be bent more like so, because the bulk of these should be so. If you temper, they should be touching each other, but they should not be touching in the default position. Yeah, something like that. And we also have some fuses, and they are of course on the power supply. And T1, what's the T1? It's this one. It's adjusting the speed of the numbers that is changing on the displays. And T2, this one changes the speed on the payout. If it's too fast, it doesn't do it right. And this one is adjusting how far the display in the othermost port should count, and this adjusts how far up the ports in the middle should count. And we do have some LEDs here. I'm not sure if the same LEDs on everyone, but let's see. The one LED is this one. Lights when the connection between the switches on the two other ports in each side is okay. That will not, since we have no game connected, it won't light up for us. And these lights, now the connection between the switches in the three middle ports is okay. And 5 lights up when the optocoupler on the they call it the magazine cover. I do think this is the input when it's entering a coin. And this should be lightning when there is payout, and I'm not sure, but this probably should count when there is a coin in the game. And 9, what's 9? It's on the power supply actually, and we don't have the power supply, and 10 is power supply, and 11 is power supply, so they don't apply to us. Yeah, so these lights is just for fault checking of the external circuit. It's not going to help us on the internal circuit. And we saw that on the other card too. We can jump some of the connections here and these lights would light up. But it also means that some of these also might affect the working of the game itself. Yes, then I'm back and I've connected some power to this card, and this is one of them that had a description of the fault. The numbers on the display is okay. No signal to the counting. The counter that is counting for payout probably, because it says payouts, and no magnets is hitting, and that is these outputs here. That is driving solenoids. And I've connected here my logiq probe. That will be the main tool for fault finding. And I've connected this up. This should be 12 volt, 24 volt and ground. And I have connected, just as now when I'm testing logiq, I have connected 12 volt to both of these. But I will add this to at least I need 18 volt or something. But just to measure out the logiq levels, this will be just fine. And this is my trusty old logiq probe from way back in the 80s. And I'm going to use this to fault find this. And there are some chips in sockets here. And if I test some logiq levels here, this should be the 4006, should be an inverter. Just to test something. Where do I have one of those on this board? Yeah, I have to check. It's the this one is a 4584. It's the same as a 4006. Okay, so here we have some pulsing. This is an inverter with input on pin 2 and output on pin 3. So these should always be the opposite of each other. This had a strange sound. Maybe it's a pulse. And this is pulsing on the input and nothing on the output. So this is suspicious right away. And I always measuring more than once on these. And to help me with this, I've done what I did on the last time we looked at one of these boards. I have made myself some short leaflets here with characteristics and truth tables for these chips. And I also marked this is the 4013. That is a dual D-type flip-flop. And you can see here where these chips are placed on the board, and the pinouts, and what you should expect of the truth table. And I've done this for every chip. This is the 4019. That is a quad and or select gate. It can both be an and an or. And the 4022, this is a chip we didn't have on the last board. It's an octal counter. And the 4024 we did have. This is a ripple counter. this actually was one of the faults with the other board, because one of these outputs was not working when you apply this for 12 volt. 4071 and 4072. It's 2 input and 3 input OR gates. 4073 and 4081. It's the same. It's C-Mos AND gates, and it's 3 and 2 inputs. And here I marked the yellow ones is the 4081 and the red ones is the 4073. 4093, it's a Schmidt trigger AND gate or NAND gate. You can see that it's inverted on the input, and you have the resettable up-down counters 4516, and there is a lot of them on this board, as you can see. We do have 10 of them on this board. And you have the 4518, that is a dual up counter, and these are clock triggerable counters. And I also have the timing diagram here, so I can see what's happening and with what signal is triggering what. And this is the mono stable trigger. It's that you trigger an input with a short pulse, and it will stay for a set time period, the output. So this is used to minimize prel, where you do have some bunching on contacts, or you can use it to set a fixed reset or other signal at the start. And yeah, you have the 4518 counters, and this was the one I was measuring on now. And on some of these boards it's the 4106 that we also had on the other board, and we also have TC 4584. That is, it's basically the same circuit. I don't know if there is any functional difference, but it's a hex 6 in a package inverter with Schmidt trigger inputs, and also the MC14 584 is the same circuit, and they are using Schmidt trigger oscillators on these. And what is causing the things to oscillate, I'm not sure, but they either use this or the other Schmidt trigger. It was this one, the 4093. I don't think there was any other Schmidt triggers. No, it was not. So the clock circuit, there is no CPU on these cards, so everything is dealt with ordinary logic. And as we remember from last time, there are some displays, I think it's 4 and 4 displays, that is counting the same sequence. And you have 2 oscillators, one for doing the counting and one for doing the swapping, for which display is showing what. So around here somewhere, 40. This is an inverter. You also have some bodge wires here, and this is a version 3 of the card, and this is a version 4 of the same card, and there is no bodge wires here, but I've not gone into depth in that. I do suppose that the board was working as it was. This is also an inverter for the 106. And as you can see, you have the input on pin 1 and output on pin 2. And here I have pulse on the input and low on the output. And here also it's the same, it's high on both input and output, and low and high. Oh, low on both sides. So both this and this one here because here you have pulsing on 5 and 5 is this one and then 6. Maybe I'm doing this wrong. 2, 3, 4, 5. Ah, yeah, 1. I was doing this wrong. Yeah, I was doing this wrong. 1. Yeah, it looks better. You do have some pulsing action here that is not in sync, but it might be used for the oscillator, so that might be okay. So I have to measure out every one of these, and this was one chip that is used for clock circuit. And you do have this. This is it seems like a digital switch, and this is for resetting the counters. Yeah, this is for setting the stop action or load action for the counters on the displays. And these are the potentiometers for setting the timings for that's clocked into this. And let's see, 4013. It's dual flip-flop, probably used to it used to divide frequencies. Each flip-flop is dividing the frequency of the clock by 2. So probably I could have measured this with frequency counting and seen what frequencies stuff is oscillating on. And if I isolate what circuit is done for the oscillation, it's probably this one here. This is the output of one of them, and if I put this meter here on hertz, I might be able to measure this frequency. No, I'm not. I also had a frequency here. Both of these should have some . You know what? Instead of using this meter, let's switch to this one. This is my old scope, fluke meter scope. Yeah, how should I put it so it will be visible, the display? Maybe if I put it like so. It's very reflexy surface here, and I do need to have my work lights on, but we can check. Let's put this into common, and as you can see here, you see the trigger, and this is probably the sawtooth on the output. Yeah, I'm not buffering this anymore, but at least I have this one, and here I also can show that I will measure in hertz instead. And it's 446 hertz on this one. And let's see what we have up here. 58 kilohertz. Yeah, 57, 58 kilohertz. Yeah, you probably will be able to see it about like so. So we do have some switching action going on here. And yeah, I know we do need to have two oscillators, so maybe we should just follow some of the leads. Or maybe it's quite obvious that one of these oscillators is going to be on this 4093. Very low frequencies. $28 kilohertz. A very low frequency. Yeah. Yeah, so the high frequency is probably starting over here somewhere, and we do have oscillation, so we do know that that is working. So what I will do now is I will take this datasheet and I will try to test each and one of these chips to see if there is something illogical going on. And by that I mean, if I see the truth table for each of these chips and I try to look at this chip here is the 4013, and we do have 6 of them on this board, and I will check here if this is right, if the res is low or high, and I will pick the field that is the entry in the table that is measuring up, and check if the outputs is okay. And of course it's difficult to do that without measuring all the inputs at once, but at least I know if every one of these is stuck low and it does not toggle with the clock, then something is wrong. So I will try to make sense of this, and I do need to pick out if there are some of these that is not used in digital fashion, because CMOS logic is also working as analog circuits if you drive them in the in the middle position. So if you feed a CMOS circuit with some levels that is in the very narrow illegal band. They actually do have some analog unpredictable output. But this is the 4013, and let's check out one of these just to get acquainted with this. 1 and 2 is the outputs, and that is the inverted and the normal. So they is the opposite of each other. And the other flip-flop have their output here. So this is the Q2 and this is the inverted Q2, so they are the opposite of each other, and that is okay. Voltage is okay, and if we measure on this first one, this should be clock, and it's working. And this is reset, and it's sticking low, and you can see here reset sticking low. It's the way it should be. Then the circuit is working. And also set, which is this one, should be set to low. So we have one of these down here, and you do have data. Data is pulsing. Yeah, they are probably connected together. Well, they are not together, so they are making some logic on this input. But let's check the other. This is set to, it's set to low, and data to is set to low, and reset to is set to high. So high reset and low set, then it doesn't matter what the clock, because this is reset. And then the output, this one should be low and this should be high. So this chip is working as it should, and we do have a lot of these. So I'm going to quickly check these two and these 6 chips and see if they work as they should, or as expected, I should say. This has quite a fast clock. And it's also toggling the reset line. The data is set to high. The set is set to low. So low, high is this situation here, and then you are toggling on the reset. So that means each time the clock is going high, this is going to be high-low. And the outputs is, they should follow. And this one should be low. Data, they have some pulsing action. Pulsing action on reset. High frequency pulse on the clock. And this will be a mix of these signals. So this also appears to be working as it should. This is using also the reset and the clock together, and that means we have a mix of these two here. And that we have, and this is the inverted signal. So this also appears to be working. And this one. This is pulsing on the clock, reset low and data high and set low. So set on reset low and data is high. It's this situation, and then the clock, positive flank of the clock, is triggering the outputs. This is kind of strange. If we take this again, this is the set signal. It's low. Data is high. Reset is low. So low, low, high. And then a positive flank on this should trigger this so that it will be set high. And then the Q1, this one should be high, and this should be low. Yeah, and since all these are tied as this should be, the first positive flank will trigger this like so. But here you can see that the negative clock flank should be, yeah, so it just stays the same. Yeah, then it's working as it should. And this one has the set signal low. And the data is high. And the reset is low, same as the other one. Clock is pulsing. And this is low, and then this should be high. So this also appears to be working. And we have this one. Low, high, and pulse on reset. And pulse on clock. Yeah, they appears to be working. And here we have set high, and data is pulsing, reset low, and the clock, then both of these should be pulsing, and they are. And there is one more to check, and it's this one. Low, high, low, and low. Then you have the high one was the data. We have this situation here, and we have only low on this, so that means that these inputs here, this should be high and this should be low. Yeah, that port was working. And if I check this one, low, high, low, then we have this again, and I have pulse on clock, and we have the low high situation. Yeah, so all the 4013 appears to be working, and I will do this with every chip on this board and test it out. I will just do it off camera, and I will connect up with you if there is some interesting development here. Here I found something interesting. This is the 4518, and as you can see, it's a clock. It's a counter circuit that is triggered by a high pulse, or a low pulse is making no change. And you can say here that you can have the the positive flank on the clock, and you can have the negative flank on the enable, and that means that the clock should be 0 and the enable 1. And the reset here is set so that if the reset is high, it doesn't matter what's on the inputs, all the outputs should be 0. And if I take this circuit here, you do have, this is the VCC, and you have the reset on this one is high. And when the reset is high, it doesn't matter what these are, all the outputs should be 0. And if I measure on the outputs, on pin 14 here, I do have low. On pin 13 I have low. On pin 12 I have low. But here on pin 11 I actually have a high, and that does not seem right. And here there is a pulse, and the clock B is tied low. So this one is kept high. It might be some pull-up action on the output that does this, but it doesn't seem likely. And also on the inputs on this side, this is the clock A, it's low. You have the enable A, it's pulsing. And you have the first clock, the second, output clock Q1, Q2, Q3, Q4. Like this, so this is doing about what it should. And this, and if we take this circuit up here, this is low on the clock, pulsing on the enable, pulsing on the first, pulsing on the second, pulsing on the third, and it struck low on the fourth. And it might be that this is resetting itself so quick that it doesn't count on this one. But then this reset has to be triggered and keeping this low, because I do have a reset that needs to be high. So if I take the reset on this 7, each time this is pulsing high, it should put all these to 0. So it might be that is happening. So this is triggered to 0 too early. But it's kind of suspicious behavior. And this is what happens when you lack a schematic, because this could be totally normal behavior, but as we don't know how this is connected together, we don't see the patterns that is able to reset this, and we don't also have a logic analyzer where we can put all these traces on top of each other to see the timing on each pin. So I'm not sure what to think of this. I can of course lift the reset from this and see if it's then counting up more. These circuits here is very prone to static electricity, so desoldering these chips and soldering them back on if you don't really need to do something, I don't think it's very wise, but I do have most of these chips laying about, I think. So it might be wise to do that. And I also have one more of these. It's the 4518, it's this one. This is pulsing on the reset. And it's counting on all of these. And this is the enable, and this is tied low. And on this side, low, and it's also using the enable. Okay. Q3 and Q4. So this is also reset so quick that it doesn't have the complete counting cycle. So maybe this is okay. This one with a high reset and a high output on the Q1B, that does not sound right. I do think I will desolder this one and check if it's working as it should. Yeah, what did I learn from this? Yeah, I can tell you. When I desoldered this, I saw the connections that was made underneath this counter here. And what this actually does is that it links from the Q3 counter bit to reset. So this resets when it's counted to 111. It's the state that we have here. This is 1, 1, 1. It's the 7. All these are at 1. And then this is pushed further to the reset signal here on A. And reset. Then this is zeroing out. So I do think that this is working just fine. And I have the same with this one. So this is a clamping diode here, and this is a 1K resistor that connects the reset to this counting digit. So I do think the 4518s also is working as they should. And I've soldered in a socket here and kept this circuit. And what's next? Oh, this is a very difficult beast to test. I don't think I will be taking that first. This is the monostable multivibrator. Oh, I did see some glitch here from the camera. Yeah, we can test the 4016s or 106, I mean. And I have one here, and this is high, low, high, low, low. Is this set as an oscillator? I don't think so, but we can test it. Yeah, let's see what the scope meter finds. It's still on hertz, and it was this one. and it's 58 kilohertz. And this one, yeah, it actually is a sawtooth. So this looks like it's running as an oscillator, and we will then be able to pick this output. This is connected somewhat to an capacitor that is growing to ground, and a resistor from this pin to this pin. So do we have that? Not exactly as I would think, because there is a resistor here, just 1K, but that is from pin 1, and pin 1 is input to another. Let's see what's... Yeah, this is just sticking to a high level, and of course this is sticking to a low level then. So this is the 58K output from an oscillator. I can of course disconnect this and only use the ohm meter to find out what else is connected to this output here. Yeah, at least there is a lot of pulse action going on. I can measure this with oh, this is not right. This is not 22 megahertz. I'm on the wrong chip, of course. Yeah, this was a special pulse, not some burst negative. Of course, then we should have the burst positive here. Okay, yes. And we do have oscillator here too. Yeah, 1.96 kilohertz. And of course, this will be the inverted of that. And we had here a bit unstable. This is not a stable signal, this is just noise. What did we have here? Yeah, this was not oscillating. And if we take the next of these, the next one is this one. Okay, this has a high input and a pulsing output. High input, low output, low input, high output. High input, low output, low input, high output, high input, low output. But this one, yeah, you can hear there are some pulses there, so let's watch them on the scope meter. No, we really can't see much here. But here we clearly have a 52 kilohertz pulse, and that's on the output on this one. So this output must be connected to something, and this must be wired together to another input. Let's see if we can find it. pin 2 on this one. It's connected to this resistor. It should be the same. Some strange behavior here. Oh, sorry, my mistake. This was not properly connected. I will measure again. It was here. Yeah, then it's okay. This is the same as we have here. Yeah, what does this tell us? It tells us that this goes further on, but I am not going to measure this out. But if this is the only connection we do have here, it's connected to some other input too, and they are just linked together. I just discovered something really strange. This board is the note that it doesn't switch the relays or the solenoids. And when I turn this board around and look into my magnifying glass, don't know if you can see anything at all on this through the camera, but these pins here, this is not soldered, this is not soldered, so there are these diodes here are not soldered at all, and not this one. So I do have to figure out the datasheet for these transistors, and I do have to check where this is coming from, because if these diodes is not connected, then they will burn these transistors at once, because they need to be protected from the flyback from the solenoids. So I will check what these are. These are BDW33A, and these other ones are tip 110 that I'm more familiar with. But I will just look up the datasheet. Yeah, I looked up the datasheets both for the tip 110 and for this BDW83A something, and I discovered something here. The tip 110, it is a Darlington NPN transistor. I knew that from before, and you can see here in the schematics for this, it does has this contraptions here that is a built-in clamping diode, and it says that it's used in medium power liner and switching applications. And normally when you do switching, it is to have a clamping diode to avoid reverse voltage when the coils or capacitors or other inductive loads is discharging themselves, so you have a reverse voltage. It isn't stated here what reverse voltage it can take, and of course when you do have the clamping diode, it will be shorted to ground or to the emitter. So from the collector to the emitter, it will be no more than the reverse voltage or the leading voltage of the diode, of course. And on the PW83, yeah, it's a much higher both voltage and amperage unit. It can sink 15 amps, while the tip 110 only had 4 or 6 or 2, depending on the production numbers. And here it is stated that you do have an unclamped inductive load energy that is 100 millijoules, and I does not attempt to relate to how much that will be, because then you have to know the inductance of the load and the voltages involved. But what is clear to me when I'm reading this datasheet is that this has no built-in clamping diode. So I can understand that they have emitted these diodes on the TIP 110 versions of this board, but on the BWE83A, we must include this diode. But there is also one other thing with this diode. This is a board that does not have the closest specifications, of course, but even though you are meant to clamp for not destroying the transistor, you also will have some inducted voltage on the CMOS circuits, and they are very prone to breaking when they have all kinds of noise on them. So maybe that's a reason something breaks. I'm not sure, but at least there is no clamping diodes on these ones when they are not soldered in on one side. So we are going to fix that by soldering in them, so I set back to the bench. Yes, I got this form here from the guy that owns these cards, and here it's mounted what some of the chips does. And this is the chips in question down here, and they say that these chips is for payouts, and these are counter chips. This is the 22s, it's these ones. This is Ripple octal counter, no, not Ripple, octal counters, and those chips are probably working as they should. I think I measured them out. And we have the 4072s. 4072s, that's the quad input OR gates. And you have the 4081s. And 4081, that is this one. It's the dual inputs AND gates. And we do have 3 of those AND gates. We have 2 of these and 2 of these. And just let's make a quick measurement on these. The 4022s have 2 not connected, and then I can show you how it should look with the logic probe with a not connected. If I move it along here, oh, you came to the not connected and it's not showing anything. And that means that this is floating. And this is the outputs. Johnson action counter, it's Q1, Q0, this is the Q and Q, so the outputs is here. Output 1, 0, 2, 3, so this counter is actually showing a value somewhat. And let's see on the reset. Oh, the reset is high. Let's see what's happening here. If the reset is high, selected output is Q0. So Q0, if the reset is high, Q0 should be the only one that is high, and that is pin 2. Okay. And Q6 is also high. And what about this? Was not connected, and this is low, and the reset is high, so also Q6 should be low. So that was strange, but this should be high and the rest of them should be high. But let's check the other one. High, high, low, Oh, here you have something that's not connected. It's an output, so of course it can be not connected if it's not used to anything. Let's check the reset here. This is also acting kind of strange, because when the reset is high, only Q0 should be output. And here they stated actually not connected, so this is counting like a ripple, like so. So this should be kind of the something as running lights or something. When you clock this, you should make the data that is coming in here like so, but I did think that the reset should make everything low. And these are acting kind of strange. I can of course take them out and see if these are testable in the retro, no, not the retro ship tester Pro. I can check it on this one, and yeah, I can of course do that real quick to check if they actually are just turned on off power. I can also just have swapped them from one socket to another to test, but let's just test them real quick. I don't have some screen capture for this now, so yeah, the 4022, and it worked, so this is perfectly okay. And this one, yeah, so both of these was testing okay, so they are actually working as they should. And this is the problem when you are trying to fault find on other people's logic and counting. I'm not sure. I can of course do a lot and lots of continue to measuring here to measure out what everything else is connected to, but in these cases where the chips are in sockets, we can of course test them and see. But first, let's take a quick view on the 4072s. They of course have a lot of sheets here now. There they are. The 4072s. This is this one. It's a 4-input OR gate, of course, and the output of this is this pin. It's low. That means that every one of these should be low, and this should be not connected. Yeah, I can just test the bottom one of this. Yeah, everything is low, and I check the top one. This should be the output. Output is low, then everyone else here should be low. Oh, here I have one that is not connected. And that is not good practice to have an input floating, especially on an OR gate. This needs to be checked out. Yeah, this turns out to measure okay. But this one floating input, kind of strange. I can of course just make a quick test on that too. It says that it's not recognized. Let's try again and see if I can find it manually. All vector testing normal, it says. But we know that this is not infallible. But if I turn this on and measure on the socket, this is the voltage in, and this is the output. It should be floating. 1 input, 2 input, 3 input, 4 input. Okay, so now this is testing low, so this is actually connected to an output somewhere. But why was this drained like so? You actually have the same down here. Strange things. I can of course swap them out and see if they behave differently. This one was measuring with one floating input. And is this now changing? Then we know something's not right. Let's see. Okay. Now it measures just fine. This also. This chip is faulty because the fault with the floating input was actually following our fault finding. So I mark this as bad, and I need to see if I have another 4072. Actually, I do have some parts board, so I can test that. This is the designated parts board, and it's an earlier revision of this board. It doesn't have all the outputs here, and it's also missing some of the ICs here, but I have taken out one 4072 chip from this, and this is an older part. You can see this is a silver plated chip, as it has the silver plating here, but we can just test this chip in circuit to see how things goes. Of course we can clean the legs better if we don't get the desired result here, but if I now test now this is testing okay. So I will mark this as changed like so. And now we actually fixed 2 faults on this board. We have done the soldering here. I can actually see that some of this soldering I soldered from the underside, but some of the solder had leaked through and made some blob on this side, so I will fix that. But let's continue. The last of these is the 4081s that is over here, and 4081s, what's that? That is a 3 input AND gate. No, it's the 2 input NAND gate that is the 4081s. Yes. So if we check that, let's see, it's first too low should be low, and the next one, this is the output, so low, then this is low, okay. This is a floating input from a 4081. Floating input, this is VSS, and this is input 1 and input 2, and so this was strange. And on the other side it's VCC, and it's input 1, input 2 and output all low, and then it's input 1, input 2, output 3. So this has a strange disconnected leg. And what about this one? This is has an high input, low input. This should be low, 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 high, low, and low. That's correct. Low, 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 and okay, another disconnect. Yeah, another disconnect. This has to be looked more into, and just do this too real quick. Yeah, it seems okay, but these two, kind of suspect. Last night I was putting this one in a socket, and it's not really that one. It was this one that I put in a socket. And I didn't feel very confident in this, and especially not since I tested the chip in this one, and I tested some of the other chips now in the same manner here, and this is not able to find fault with C-Mos circuits, because every one of these was testing okay, but in real life they was not. So I put in a new chip, new old stock from back in the day, and let's turn this on, and I can show you what I have. This side is low on the clock, enable is pulsing, Q1, Q2, Q3, Q4 pulsing, and reset pulsing, and of course VSS is low. And on this side you have the clock stuck low. You do have the enable pulsing, you do have Q1 pulsing, you do have Q2 pulsing, and Q3 and Q4 both stuck to 0, and you have a pulse here on reset, and of course VCC is high. So that's with the new circuit or new IC in place, and this is the 4518 or 14518, as was the original chip. It's the same chip, of course, but different vendor. This is a desoldered chip, so I'm using a machine socket, so it should be easier to get it in there and get some measurements. And let's see, this side, low, pulsing, 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 and low. So that side is the same. Low, same as the last time. Pulsing, same as last time. But here, it's stuck high. This one was pulsing, this is Q1. This is stuck low, this was pulsing. This is low, is the same as the other. This is low, same as the other. Reset, stuck high. This was pulsing on the other one. So even though this programmer, the 866 Pro, it's not Pro, it's the 866 2 Plus. It's the original one. And it tested this chip just fine, but clearly it's bogus. So let's put this back in, and I have now tested with the logiq probe all the circuits here. There is no more floating pins that I don't have an explanation for, but of course I can't follow every signal on this, and ideally I should have recorded every signal on every pin on this one to have it to fault find on the two next boards. But I'm going to ship this back to the owner in Bodø, and he will test it in his coin game. And if it's not working, he will make a new description for me and send it back. But the fault is quite numerous that I have fixed on this. This one, of course, but also these three here. And a lot of these transistors was not soldered in one of the pins, and two of the diodes was not soldered on both sides. One of the diodes here was soldered only on one side, or two of them was soldered only on one side. And if you have transistors like this is quite powerful Darlington transistors. That's a double transistor that's coupled in series actually in here to have a more powerful switching circuit. And when you are using this to switching a magnet or solenoids with an inductor, you need to have a diode in place to short circuit the flyback voltage that is coming in reverse when you turn off the circuit. And as long as these diodes was not properly soldered, I do think that's what's destroyed these, because it's coming a reverse pulse that is much higher than the C-Mos is able to handle. So these should have clamping diodes. It's all the B variant of this, but it has to be tested. So what we are going to do next is that I'm going to fault find on the rest of the boards, but I'm not going to do anything before I hear back from the owner of this board, so that we can have a good comparison. And also when he has a working circuit down there, I can ask him to put a meter on it or something to measure pulses or measure voltages on some outputs if I'm not sure. But I do think we just wrap this one up and we will get back to fault finding CMOS circuits on the next two boards. And I've learned a lot about this. It's never easy to fault find on circuits where you don't know everything, but my approach here has been to take the individual chips and see how they fare there. And I can also take this one when I'm here. This is also a 4518. All the same as the other one. I measure exactly the same as this one. So hopefully all the circuit is okay. And I've done this on all circuits here now. I've tested the logical levels, but of course they still can be damaged because I can't test them in every situation. An AND gate, for instance, if it has a 0 and a 1, I am not simulating and putting a 1 on the circuit to see if the output is switching. I'm just checking the solid state that they have now. And of course, when there are pulses, I can check them as they should, but not on the static level. So that's it for this board. I'm going to clean the desk and put this aside until I hear back from him. And you will hear the report on the beginning of my next video with these boards. And this is the Lars Berg boards from Norway, from the automat or knipsekasse or coin game, SilverCoin, I think it's called. Yeah, this is Koiro from Mars 2026 that is back again. And just to give you a short update, I said in the end, or the last clip in this video, that I was going to publish the news about this in my next video about this project, but I'm going to do it here instead. So spoiler alert, or not spoiler alert, because everything is about this board, but it's working. He had some troubles. I actually was in my hospital bed when we had this discussion via Messenger, and he told me that he had some problems. He didn't get it to work, and I was kind of dissatisfied. He said that it wasn't working, that it had about the same errors, and I find that strange. But afterwards he did some magic to some other things, maybe some bad contact points or something on his coin game, and he actually got this card to work. So that we know that all my repairs on this board actually made sense. And it could be that some of the fault that I was fixing with these chips, didn't affect everything on this game, so he was not able to test it. And also it could be some slight mismatch where it did work in some instances and not in some others. We had that when we fixed this kind of board before, where we had this chip that was working when you lowered the voltage, but when the voltage passed 11 or 12 volt, I don't remember, then it stopped working. So this CMOS logic is kind of strange, kind of difficult to fault find. So the logic probe is everything when you are doing this, and you also have to double check every check to make sure that you actually are getting the results right. So thanks for watching. I'm going to fix all the other boards too if he asks me to, but I'm going to have that discussion later with him. But as of now, this is the last video I will be filming here exclusively from the garage. So hopefully I will be back on my feet over the Easter holidays, I hope. So thanks for watching, hope to see you in my next video. Please hit like and subscribe. And as always, thank you.